Oh, hi. You caught me doing what I do every day, all day, looking at really interesting rocks. And that's what we're actually going to do. We're going to actually turn to the rocks and the rock record or the geologic record to look at our next topic, which is climate change through time. So we've had a really good look at the modern climate system, atmospheric circulation, and atmospheric composition. And what we're going to do now is look at how that's changed through time. So we're going to look at principles and approaches to the problem. We'll look at things from the 10 million year to 10 billion year time scale. We'll then narrow it down and look at it from the 10,000 to the 1 million year time scale. And then we'll look at things happening seasonally and decadally. We'll look at the concept of abrupt climate change. So our learning objective throughout this topic and topic 10 as well is to understand how climate has changed in the past and what drives those changes. All right, so we're going to start off with our principles and approaches to the problem with our classic question, why bother? Why should we bother studying ancient climate? You know, you could state this another way and ask, who really cares what happened a really long time ago in terms of our climate system? We're going to go back thousands, tens of thousands to when there were just very few people around to impact climate. We're going to go back tens of millions of years to billions of years even to look at how climate has changed through time. Who really cares what happened hundreds of millions of years ago when there were no people around? Does it matter? Well, yeah, actually it does. So we should really worry about this issue and try to understand Earth's past climate for a number of reasons. Number one, past variability can show that there were extremes in Earth's climate, even greater than today, in terms of how fast climates change, perhaps in terms of the magnitude of the changes, than any we may have experienced in our human recorded history. We also can ask the question, what was the planet like? What was the Earth's atmosphere like? What was the climate system like well before any humans were here to perturb the system? Because that may be the best way to truly get what the baseline non-human component of climate change is. There's perhaps a lot of skepticism about the climate change we're seeing now, that it may be just part of a series of natural cycles. If we don't understand what the pre-human baseline was, we can't answer that question as well as we possibly can. We might also ask the question, how periodic is climate change? You know, we're in a warming cycle now. Is the warming just part of a cyclic period and eventually things will turn around and go back down and then we'll be okay? Or are we on part of a trend that's unprecedented and not cyclic and not going to sort of self-correct? So by understanding ancient climate, we can gain insight into all of these questions. So we've probably answered the why bother question well enough to say, yeah, let's go ahead and consider this topic. So we have to consider factors that have been influencing climate on various timescales. So we've got greenhouse gases. We're aware of that from our study of the modern climate system, how important greenhouse gases like carbon dioxide and methane and water vapor are. And so one question is have these greenhouse gas concentrations in our atmosphere changed over time? We saw a few topics ago, plate tectonics, that was an important driver of moving volatiles, including greenhouse gases, from the Earth's interior to its exterior through plate tectonic activity. When plate tectonics is more active, there is more of these gases being put into the atmosphere. So there may be changes just from the actions of plate tectonic in terms of the levels of greenhouse gases in our atmosphere as a function of time. Solar energy may change through time, the output of the sun and the incoming solar radiation. Changes in the Earth's orbit. As the Earth goes around the sun, its orbit is just not stationary and static through time, but as we'll see, it actually changes. This may have an influence on climate as well. And one last interaction we'll look at that affects climate is interactions between the oceans and the atmosphere and feedback mechanisms between the two that affect changes in our climate system. We may ask the question, how can we reconstruct changes in climate through time? How can we do this? How can we put this together? Coming to the rescue are geologic records of climate change. All right, so if we consider geologic records of climate change or environmental change, these are also known as climate proxies in quote, just like when you would go to to vote and you're not going to be in town, you can vote by proxy because you're not there. Well, we weren't around a really long time ago. We didn't have thermometers, we didn't have rain gauges, we didn't have instruments to record, we didn't have people making observations and recording it was really rainy today, or there was a hurricane here during this time. Those records go back 100 years, a couple of 100 years, in some cases, maybe hundreds of years, depending on how advanced the civilization was. But beyond that, the data accuracy, reproducibility, validity really fall apart. So instruments weren't around back then. We have to go to some other way to record climate, and for that we go to these climate proxies or geologic records of climate change. And we'll explain what those are in just a minute. There's actually several different kinds we may have. We have sedimentary rocks. Yeah, sedimentary. We may have fossils. We'll look at examples of that. Ice cores, tree rings, speleothems or cave deposits. And in all of these things, and we'll go through examples of many of them, keep in mind that requirements for these things to be valuable climate proxies is, number one, there's some way of telling time. There's some way of knowing at the time scale, both absolute and relative, that we have in these particular proxies. And the other requirement is that they record somehow, some way, perhaps in their chemistry, a signal of climate change through time. All right, well, who reconstructs geologic records of climate change? Anybody? Who would reconstruct a geologic record of climate change? Well, perhaps geologists do. Let's take a look at what a geologist really is.
Are you okay?
Yeah, I think so.
Oh, thank God he's all right.
Look, it's the Langley Falls town geologist.
It's true what they say about geologists. They're the coolest, sexiest men alive.
The rest of this pit will collapse any moment. We have to get that man out of there immediately, or he'll be buried alive.
We fill that hole with foam, your man will float right to the top.
I don't think that would work.
Neither do I, but I got a truck full of foam and 6 kids to feed. Come on, I need this.
Why don't we just lower a rope?
A rope made of foam?
Stop, okay? Just stop.
Tie yourself on!
Okay.
Stan, I thought you were dead. Oh, thank God.
Hey, where did everyone go?
Oh, the geologist took everyone to the Waffle House.
Before they even knew I was okay?
Have you ever had breakfast with a geologist, Stan?
Good. Okay, well, welcome back. Now that we know what a geologist is, we'll now go through some examples of these proxies, these geologic records of climate change. The first one we talked about was a sedimentary rock, but now we'll turn to an organic deposit, coral reefs. So you could see from this image that coral reef is growing at the margin of oceans in shallow water, depending on the species. The depth at which they can go varies. The ones we're going to be concerned with live in very shallow water. They're almost acting as paleo tide gauges. They tell us where sea level was, and they have a way of recording changes in climate even further than that. So the coral skeleton, coral is actually a organism. It's an animal. It's not a plant, even though they often look like plants. And if you enjoy snorkeling and scuba diving, when you see the luxurious colors, you really think they're some kind of plant. But they're actually animals. They have a symbiotic relationship with algae that makes them sort of have an association with a plant-like organism, the algae. The bottom line here is, for what we're going to be talking about, is that the skeleton of the coral is a mineral called aragonite. Calcium carbonate is its chemical composition. Aragonite is the mineral name. It's a hard, stony skeleton. I would not bash this against me because it would scrape me. If any of you have surfed and wiped out on something like this, you know how hard and stony these things can be. We're going to learn a lot more about corals in our topic on sustainability of the oceans. But for now, we're concerned with how these things are recording past changes in climate. So this stony skeleton, this mineral that's precipitating, season by season, as these organisms grow, they're growing out of these little polyps. You can see little holes here, and there's actually nothing in the hole. All that's left is the hard skeleton. So this sample died a long time ago. Bacteria, when it was laying on the floor of the ocean, consumed all the nice fleshy parts. And all we're left with then is the stony inorganic mineral skeleton that makes up what we have here as actually a sedimentary rock. It's formed by sedimentary processes. Wave 2, chemical precipitation from the oceans. And chemical precipitation is the key here, because as this mineral precipitates, as the skeleton is growing season by season, temperature may change seasonally, and that temperature change changes slightly the chemical composition of this skeleton as it incorporates ions from ocean water. The changes are small, but they're readily measurable with modern instrumentation called a mass spectrometer. And those slight changes in chemistry relate to slight changes in the temperature of the surface of the ocean where the coral was growing. So these corals are recording past sea surface temperature through their chemistry. So that's how it records the climate signal. One kind of coral. This is another species that's particularly hard on surfers and is particularly robust and can live where wave energy is strongest. We'll return to that when we talk about sustainability of the oceans. And here's yet a third species of coral. And like all the others, you can see these holes where we're just left with the solid mineral skeleton, not banging my head with it because it's going to hurt. The fleshy parts are gone. We call those the meat holes. That's where the organism was living. It's a colonial organism. And you can see there's literally hundreds making up just this fragment of what was once a large, perhaps 2-meter wide head of this domal type coral. What you can see in cross section here are these lines. So the oldest layers are here, the youngest are up here. In a lot of species of corals, these sorts of stratigraphic lines are giving us indications of the seasons. So every line here we see is a change, an annual change. So we could count backwards through time if we sample these things, known date that they're living, have independent means of dating them by radiometric isotope methods. In any case, there's time for it. So we have time, and we have the climate signal of the change in chemistry telling us about the sea surface temperature of the oceans. These sorts of climate proxies have been used to test and reconstruct past models for how El Nino, La Nina climate cycles have been forming and how they're driven by changes in sea surface temperatures in the tropical Pacific Ocean. Okay, the next kind of proxy for climate change we have are tree rings. Here's an example of a tree, and this particular oak tree is from Arizona. And the way tree ring works, I'm sure you guys are all familiar. Oldest rings in the center, youngest rings at the margin. And we can actually go through time. And the dendrochronologists, experts, and these are particular ones have been studied by dendrochronologist Dr. David Staley, University of Arkansas, as well as Dr. Malcolm Cleveland, the same university. Dendrochronologists can actually count microscopically every one of these seasonal layers in these tree rings. This particular one goes all the way back to 1834. So we know that's when the tree was first beginning. Kind of blows you away, doesn't it, that somewhere right around here is the tree at the time, the outer layer of the tree at the time of the Civil War. Somewhere not too long after that is when I was born. And when you guys were born is somewhere right around here. So we can tell time quite precisely and accurately with tree rings. The other thing that tree rings are really useful for is you can see that some of the rings are thicker, some of the rings are thinner. All other conditions being equal, this usually gives us a clue as to water availability, basically rainfall and temperature. More it rains, with all other factors being equal, the thicker a ring the tree will lay down. So these have been used to reconstruct paleo drought histories. This is an important climate proxy for telling us about past droughts. To test whether you understand this or not, to test your knowledge, look at the next image, and you can see a microscopic slide of the tree rings. And on this microscopic slide, my hand's going to wave across, and we're going to go from the oldest part of the record to the youngest part of the record, and you tell me when to stop when we get to this youngest part of this record. Yeah, right there. If you stop me right here, you are correct. You've well tested your knowledge. This thicker layer is indicating When things were wetter, these thinner layers are indicating drier times in the past. That's how tree rings work. Next, we're going to talk about speleothems. So speleon is from the Greek root of that word. Speleon in Greek means cave. And speleology is the study and exploration of caves. Speleo, because ology means the study of. Speleothems, same Greek root, speleon meaning cave, them means them things. Speleothems are them things that grow in caves. Full disclosure, I don't know what them means in Greek, but speleothems are certainly the formations that grow in caves. So for example, if we went into a cave, we might find growing on the floor of the cave these kinds of speleothems. These are calcium carbonate mineral deposits that form from water dripping into the cave. It rains above the cave, water infiltrates through the soil, then through the limestone, it drips into the cave, it loses its, degasses its carbon dioxide, that causes the chemical reaction to occur that precipitates calcium carbonate as this inorganic mineral, and layer by layer, tens of microns a year from this dripping water, the water will drip onto the surface, spread out, form a thin film, and then an incrementally small layer of the mineral calcite will accumulate each year on top of that. It accumulates continuously. In contrast to tree rings, if a tree we find in Texas is 500 years old, we get pretty excited. Speleothems can grow continuously in one spot over tens of thousands, even hundreds of thousands of years. This sample right here, for example, grew over about 50,000 years of geologic time. So if we were to come into a cave, we might see things such as this growing off the floor of the cave. They're called stalagmites, the way I remember it is. It might make it to the ceiling one day if it continued to grow. Or they might be stalactites if they're growing down from above. They're hanging tight to the ceiling, stalactites. So the question is, are these tights or are they mites? And one way you might be able to tell is to take a look at the layering that you see. The one on my right, your left, has really distinct layering in that you see very high angle and extension of the uppermost layers here, whereas the one in my left hand on your right actually has much flatter layering on top. Which one do you think grew from a drop of water falling and spreading out, growing the mineral deposit like that? And which one do you think formed from water dripping from above and the water droplet hanging downward by gravity, and then the calcite forming where the water was hanging down? So if you guessed mite and tight, you would have been correct. The key thing on all of this is that we have radiometric isotope methods for accurately dating the growth layers, individual growth layers in these cave deposits or speleothems. And then we can measure various chemical elements or other isotopes that occur layer by layer over a long time series. Could be thousands of years, could be hundreds, could be decades. Speleothems grow over a wide range. We can measure various chemical elements and isotopes that may give us clues as to the composition of the water and how that changed through time. So this is really nothing more than a frozen-in mineral deposit that records changes over time of the composition of the water dripping into the cave. Also, it may record changes in the amount of water dripping in the cave. Much like tree rings, when things are dripping, raining more, dripping into the cave more, these things may be growing faster. It's international sign language for a speleothem growing faster, as opposed to during drier times, they might be growing a little bit more slowly. So we can piece all of this together, the amount of water dripping into the cave and its composition, to reconstruct what was happening in the atmosphere outside of the cave. And that's how we use speleothems to reconstruct ancient climate. That's how speleothems are proxies for ancient climate. Well, if you were to slice one of these stalagmites, one of these speleothems, in this case a stalagmite, growing upward in a cave, this one's from a cave in the Austin area, you could see the magnificent layering. The layering may be due to impurities that are being washed in from the soil zone with the waters dripping into the cave and being incorporated into the calcite mineral as it grows. Note how periodic and sometimes aperiodic that this layering and this coloring seems to be. Also take a look and note that this thing is as tall as the UT Tower, which means it covers all of geologic time based on what we said before. All right, that's a complete misnomer. This is another sample that is undergoing analysis. Love to hear anyone's guess on how old this may be. I'm also holding this with gloves, not because there's anything that you can get contaminated by in these cave deposits. They're actually fine to touch with your bare hands, but we're doing research on them, and the radiometric dating technique requires that they be handled very cleanly, because we don't want to measure anything that comes off of us. We want to measure just what's in the sample. Some speleothems, if they're growing really fast, or if they're growing for a really long time relative to others, can become quite large. In this case, this sample, which we call the big boy, is approximately 2 meters in length. Analyses are underway to determine just how long a period of time it's been growing over. Be happy to hear your guesses as to what the total amount of time captured in this layered mineral deposit is. Well, one of the last climate proxies I'd like to chat about are ice cores. So you can see from the image, much like all the other deposits we've been looking at, if you have layering, oldest layers in a glacier on the bottom, youngest layers in the glacier on top, we again have a great way of telling time. A lot of the glaciers lay down seasonal banding in the ice, and then the ice might be able to tell us something about perhaps the atmospheric composition. In fact, the diagram we've looked at most frequently this semester has been this history of atmospheric carbon dioxide, the Antarctic ice core up through the Mauna Loa. Those are modern atmospheric samples of air, reconstructing CO2 on the y-axis versus time. So this is perhaps the most iconic figure in climate change science. It really set a lot of people thinking about climate change and put ourselves in context in terms of the history of our planet. And we've talked about this a number of times in terms of the scientific method, the rigor of reproducibility, that no one on either side of the climate change debate actually questions these data. Let's talk a little bit about how the data are collected and about their reproducibility. So you core through the ice as shown in the upper right image. Drill a core down through the ice, pull up these cores, count those layers back through time, have some independent means of conferring those hand-counted dates. We have a time series, and then how about the CO2? It's easy to understand time when you have these layered deposits, how we can determine that, but how do you determine atmospheric CO2 from this? So it turns out as snow falls on a glacier, as the ice is forming, it's trapping little pockets of atmospheric air. When it traps these pockets of atmospheric air, it's that layer. It's that layer that you can date that layer, go back later, dig down, and reach that layer for that particular time period, say 1,200 years ago. It was somewhere a few meters down perhaps in this ice core is where you might find that dated layer 1,200 years ago. And then scientists can go in and extract those pockets of air under very carefully controlled conditions so that it doesn't get contaminated with modern air, and inject it into the source of an instrument like a mass spectrometer, measure the concentration of the carbon dioxide in that pocket of air. And that tells us the paleo CO2 of our atmosphere at a particular time in the past. So that's how that Antarctic ice core data are obtained. And if you look at this curve here, the blue curve and the red curve, this figure we've looked at a lot of times this semester, one thing to look at is that there are little blue dots hiding behind the red dots. So where the Antarctic ice core record comes to more modern times, where it overlaps with the direct atmospheric air measurements, the Mauna Loa, the red dots, right? Blue is ice, red is the modern samples of air. You could see that they're right on top of each other. The blue are really hard to see because they're directly overlain by the red. Think about the reproducibility of that and the rigorous approach of the scientific method here in evaluating reproducibility. You go down to the bottom of the planet, you core down through the ice. You count back decades, decades, decades. You measure the CO2 through this air pocket extraction mass spectrometer fancy method. And then you go to the top of a mountain on an island in the middle of this ocean, nowhere near the bottom of the planet. This is more in the middle of the planet, on the top of a mountain. Capture atmospheric air there, make those measurements over time, and you get them exactly reproducing. I mean, these things, these methods of measurement, these locations couldn't be more different, yet they're right on top of each other, showing the rigorous scientific method being applied here, and why no one on either side of the climate change debate, if there is one, doubts the validity, accuracy, and precision of these data. All right. Well, so here's a research station in one of the polar regions. I've never been to one of these, but people who I know who have been tell very interesting tales of what it's like to do research. They're kind of sunken down into the ice, little roofs and walls put on top. Apparently, if you don't like the size of your office, you just go borrow the chainsaw and go up against the walls of your office and shave it back, and then you have a larger office. Okay, well, so those are the various ways we can reconstruct past climate change. I've showed you samples of all of these proxies, from sedimentary rocks to corals to tree rings to speleothems, mite and tite. Now let me show you a sample of the ice core from Greenland polar region. Got it right here to show you. Oh man, I forgot the cooler. Damn. National Science Foundation will never fund me again. Don't be alarmed. I was just kidding about that. Okay, so we've gotten over that, and now we can move onward. So the first thing we're going to do is go back in time to reconstruct past climate and show some examples of that. So before we go back in time, we have to have our time scale down. So the next image you're going to see is the geologic time scale. And this diagram, while complicated at first, actually becomes pretty simple once you look through it. We're going to start here with the about 4.6 billion years ago when the Earth was formed, and we're just going to go rifling through time there. The entire geologic time scale is in this left-hand diagram, right? It starts at 4,600 million years, which is the same thing as 4.6 billion years, and it's 0 at the top. That's us right at the top. Okay, now we could see those top sort of 600 million years right up there, take that and widen that up, and that's what's shown on the right-hand column, going from 600 million years ago again to today, 0 at the top. Now we've gone through a lot of geologic time just here. We're going to focus on this. These younger rocks is really the best known part of the geologic record. They tend to be more well preserved. They haven't been metamorphosed as much. They haven't been consumed by plate tectonics as much. All right, so we're going to go through that, but just one note where we came back to older rocks earlier this semester. Do you remember we came right around here 1,100 million years ago, or 1.1 billion years? Do you remember what that was? That was the age of the granite batholith, the igneous intrusion that made enchanted rock here in central Texas. Okay, we're going to jump forward and go through this time period, the last 550 million years or so. This eon is referred to as the Phanerozoic eon. The eras that can be broken out are the Paleozoic era, the Mesozoic or Middle era, and the Cenozoic, the most recent of those three eras of the Phanerozoic. And then we can break them down even to geologic periods: Cambrian, Ordovician, Silurian, Devonian, Carboniferous, Permian, Triassic, Jurassic, Cretaceous, Tertiary. And at the very top here, the last couple of million years, is the Pleistocene time period. We're going to focus on a couple of these back through here. We're going to look at the Cretaceous time period, about 100 million years ago, and we're going to look at the Pleistocene time period. And then we'll get even younger than the Pleistocene. The last 10,000 years, really hard to see here, is called the Holocene period, Holocene. All right, consider the vastness of geologic time. It's one of the coolest things, one of the most daunting things for one to wrap their brain around. That this planet's been here for 4.6 billion years, and that we could look at processes waxing and waning, coming and going, changing over these vast timescales, things that have some sort of cycling or periodicity on timescales of tens to hundreds of millions of years, to things that are varying very rapidly, by contrast, seasonally, within a year. Just blows your mind when you think about that scale.
Uh-oh. Suddenly, this meeting and all the strange words make sense.
Also blows your mind and humbles you somewhat when here we are living on this planet, being stewards of this planet. Yet, is it really our planet? How long have we been here? So if you take the amount of time that we've been here and compare it to the age of the Earth, if we look at the UT Tower, you consider the height of the UT Tower as all of geologic time, then the amount of time that we people have been here is equivalent to the thickness of this sheet of paper. So someday if you have a chance to get a tour of the top of the tower, bring that sheet of paper up there and compare that with the vastness of geologic time represented by the height of the tower. Okay, so let's consider how climate has changed through geologic time. The next figure we're looking at is a diagram that shows glaciation as a function of latitude on the y-axis and time on the x-axis for that Phanerozoic period, right? The last approximately 600 million years. All right, so when we have glaciers coming down to low latitudes, that means it's cold, right? When we have no glaciers at any latitude, like here, that means it's warm, right? This period of time back here, around 300 million years before present, glaciers coming all the way down to 40, 35 degrees latitude. That's a very cool time. Last 40 million years or so, very similar situation. We call these times of extensive glaciation, we call those time periods ice houses. The Earth was relatively cool. The times in between, we call those greenhouses. Shown in this warmer color are the greenhouses, and the cooler, bluer colors are the ice houses. So along this time scale here, you can see blue, pink, blue, pink, blue. So there's some flip-flopping back and forth between these warming periods and these cooling periods on Earth. It's not going in one direction unilaterally. It's not a runaway ice ball. It's not a runaway boiling of the oceans. There's some overall range in which Earth's climate has varied over time, and these are pretty long time scales. These greenhouse and ice house periods are tens of millions of years long. What possibly could have caused it? But first, how can we possibly have reconstructed this? What is this data based on? How can we tell where the glaciers have been? Well, one way we could tell is by looking at the marks that the glaciers leave behind. When glaciers move over rocks, they pluck up pieces of the rock and they keep moving, and they entrain the rocks at their base, so the ice sheet is moving and moving and moving, and it's got these boulders and cobbles and gravel at the bottom of it, of the rocks that they've plucked up as they've moved along with great force, and they're weighing down with great force on the new rock that they're moving over, and as they move over, they're kind of scratching them. The rocks on the bottom of the ice that it's entrained is scratching the bedrock beneath it, the surface of that bedrock beneath it, and these things are called glacial striations, or slicken lines is another fancy term. There's a couple of ways we could get those. One way is through glaciers moving over rocks. Another way is when rocks move past each other by faulting. In either case, never been around when it's happened, but you can imagine that there's probably some great sound that's been produced by the ice moving over the rock or the rocks moving past each other. It may have sounded something like or it may not have. I've never been, and I've never seen such a video on YouTube to know exactly what it sounded like. So that's a little bit of speculation on my part. In any case, these striations are left behind, and that, along with other features that are indicative of glaciers being in an environment and the environment being cool, things like the vegetation, the kinds of animals that are found, basically the fossils, these vast different records of past change, are ways that scientists reconstruct that we had these ice house and greenhouse periods in the Earth's past. So, one thing we may ask is, what might be a cause? What are the candidates? As they said in the movie Casablanca.
Round up the usual suspects.
Who are the suspects that we're looking at here in terms of being guilty for causing these changes in Earth's past climate? Well, one thing right off the bat we might think about are greenhouse gas levels in the atmosphere. So on the next diagram, you could actually see reconstructed levels of greenhouse gases in the Earth's atmosphere. In this case, it's CO2. So it's paleocarbon dioxide levels in the Earth's atmosphere from these geologic records of climate change. And there's two curves being shown here. In red is a model that's been created, a theoretical model, and in black are those proxy measurements, right? Those are the geologic records. So you can see both the model and the proxy show that during these greenhouse periods, things are much warmer. During the icehouse period, not warmer, but they were warmer, but they're associated with levels of very high CO2. Remember, today's CO2 in parts per million is about 400 parts per million. These levels back, say, in this greenhouse period about 100 million years ago, were up around 2,000, so 5 times what we see today. Back earlier, about 500 million years ago, it looks like they were on the order of 6,000 or 7,000 parts per million. Multiple times, factors of 10 or more levels of carbon dioxide in Earth's atmosphere than we have today. This apparently can explain this shift between greenhouse and icehouse climates, shifting amounts of carbon dioxide in the Earth's atmosphere. So this is quite fascinating, is it not? Would you agree?
What? No.
I'm waiting to hear if you would agree.
No. No. No.
Yes.
Okay, I think we all agree that it's fascinating.
I mean, no.
Where does the CO2 come from that creates these greenhouse periods, these warmer periods in the past? We kind of know about what an icehouse period is like because we're in one now. We have glaciers, extensive ice caps at the poles. There were more extensive times in the past, but there are times in the past, if you look at this figure right here, when there was no ice at any latitude, no glaciers at any latitude, much warmer than we've experienced today. So what caused these greenhouse periods, the buildup of CO2 in those periods? That's a first important question. The second important question is, why are there cycles? If there's some source of CO2 that was, being contributed to the Earth's atmosphere, why didn't it just continue to go up, up, and up? Much like we're seeing CO2 over the last century, and it's projected into this century, right? It seems to be a sort of a monotonic or unidirectional increase, getting higher and higher as a function of time. That's not what happened in the past. It was high, it was low, it was high, it was low. It went through some cyclic back and forth. Why are there cycles? Does that give us some clues as to what the mechanism may be? So let's talk briefly about the mechanism that might be responsible for these cycles and carbon dioxide levels in Earth's atmosphere, and therefore what would be responsible for Earth's changing climate on these timescales of tens of millions of years that we see. So the concept goes that it's actually a function of plate tectonics. We know that plate tectonics changes its sort of rate of activity, rate of seafloor spreading. Those sorts of parameters are not exactly constant through time, but they actually change. And those changes in tectonic activity will cause, during more active times, will cause more abundant exhalation of volatiles, including things like CO2 from the Earth's interior to its exterior, namely to its atmosphere. So we're adding CO2 to the atmosphere on these long time scales of more active plate tectonic periods. Okay, but again, that should just, as plate tectonics adds and adds and adds over time, it should just keep going up, up, and up. Well, so as it turns out, that good old weathering, chemical weathering and physical weathering of rocks is actually helping to keep this CO2 from going unidirectionally higher and higher. So what happens is that chemical weathering uses carbon dioxide from the atmosphere. We can write out a bunch of reactions of taking mineral formulas and carbon dioxide and water and rain, some water from the sky with CO2, or have the water go through soil and pick up even more CO2. You make a weak carbonic acid, and that weak carbonic acid can attack minerals, and that is the essence of chemical weathering. When you look at those reactions, CO2 is on the reactant side of things, but it's not on the product side of things. So that CO2 is consumed and converted into other chemical molecules, a lot of it just washing into the ocean. And what happens is that consumes the CO2 from the atmosphere. And so the way you can consume CO2 from the atmosphere is increase the rates of weathering. After you have a period of very active plate tectonics and you're building mountains, you're exposing fresh rock to these weathering processes, the weathering rates after these periods of active plate tectonics will increase. So the more active or more rapid or more vigorous plate tectonic episodes help release CO2 from the atmosphere. It builds up, things warm and warm and warm. And then as a consequence of building new mountains and exposing new crust, you're also increasing the rate at which things are weathering. The warmer climate also aids in that as well. So with a warmer climate, more fresh rock exposed, you're weathering things more rapidly, and that's going to draw down CO2 more rapidly than previously. So it's this weathering phenomenon that acts as the policeman. The plate tectonics is driving the increases, and it's the weathering that results from that more active plate tectonics that's the policeman in keeping things in check and drawing the CO2 downward. And that's why we have cycles. So to look at two examples of what the Earth was like in the past, we're going to go back to a greenhouse period, the Cretaceous time period, and then we're going to go back to an icehouse period, the Pleistocene time period. The first one's about 100 million years ago. The second one is tens of thousands of years ago. And we're going to have a look at what the planet looks like and what may be responsible for those differences. That's what we'll do when we see you next time in class. Till then, enjoy your rocks.